Reading science to pigeons. Electricity and magnetism. I will begin by speaking about electrical circuits. Electric current is the rate of flow of charge. This charge is usually carried by electrons. These electrons are negatively charged. They flow around a complete circuit. A complete circuit is a closed circuit loop. This complete, unbroken path is necessary for flow. Conventional current direction is a historical standard. It is defined as flowing from positive to negative. Physically, though, electron flow is actually from negative to positive. Current is not used up by components. The current leaving the battery equals the current returning. The total current remains constant. Potential difference is voltage. Voltage pushes the current. A battery or cell provides this driving force. Increasing the potential difference increases the current. Cells can act together as battery to increase this push. Resistance opposes and slows the current flow. It is measured in ohms. Resistance equals potential difference divided by current. This relationship is known as Ohm's law. If voltages stay the same, then higher resistance lowers the current. Conductors allow electrical charge to flow easily. Metals like copper are good conductors. Insulators do not allow charge to flow easily. Plastic and wood are common insulators. Lower resistance means better conduction. For example, a 1.5 ohm bulb conducts more current than a 3 ohm bulb. So, let me now speak about measuring current and potential difference. Current is measured by an ammeter. The ammeter must be connected in series, that is, in sequence in the circuit. Current is measured in amperes. Amperes are often called amps. The symbol for the unit is A. Current is conserved in a series circuit. Thus, the reading on the ammeter is the same as the current in the bulb. Potential difference is measured using a voltmeter. The voltmeter must be connected in parallel, that is, across the component. Potential difference is measured in volts. The symbol for the unit is V. Measure across components like bulbs or batteries. Batteries are rated by their potential difference. These ratings indicate the energy supplied per unit of charge. Bulbs also have voltage ratings. These are maximum voltage ratings. Exceeding this rating can blow the bulb. These ratings ensure safe operation. Circuit diagrams represent real electrical setups. They are simplified drawings. They are standardized schematic drawings. Start by drawing the cell or battery symbol, then add standard symbols for each component in the loop. So, let me now speak about series and parallel circuits. Circuits arrange in two patterns. These patterns are series and parallel. Series circuits provide a single path. Current follows one route only. Ammeters placed anywhere show the same reading. Voltmeters measure potential difference across components. The sum of these voltages equals the supply voltage. If one component breaks, the whole circuit stops. But parallel circuits, these provide multiple paths. Current splits into different branches. The current in the branches adds up to the total current. This total matches the current leaving the battery. Voltage is the same across each branch. Components operate independently. One light can be on while another is off. If one breaks, the other stays on. Thus, some branches may be on, other branches may be off. But what about static electricity? Static electricity involves charge buildup. The buildup occurs through friction between insulators. Atoms contain electric charges. These charges are positive or negative. Negative charges are electrons. Electrons orbit outside of atoms. By orbiting the outside, they can move. Positive charges are protons, but protons are trapped in the center of atoms. Thus, they do not move. Positive charges are bound in solids. Rubbing two insulators together transfers electrons. Electrons move from one material to another. They are scraped off one surface and they collect on the other surface. The electron-gaining object becomes negatively charged. The electron-losing object becomes positively charged. The size of the charges is equal but opposite. Consider a polythene rod and a cloth. Rubbing moves electrons from the cloth to the rod. The rod gains a negative charge, the cloth is left with a positive charge. All charged objects produce an electric field. This field surrounds the charged object. Forces can act without contact. That is, they can act without touching. The electric field defines this region of influence. Within this region, other charges feel a force. Forces act across a gap. This type of force depends on the charges involved. Opposite charges attract each other. Positive and negative charges attract, they pull together. Like charges repel each other. Two negatives or two positives push apart. So, let me now speak about magnets. Magnets produce fields. These fields surround bar magnets. Bar magnets have two poles. One pole is north, the other pole is south. A magnetic field is a region. In this region, magnetic materials experience force. Iron and cobalt are magnetic materials. Fields are drawn with lines. These lines are magnetic field lines. Field lines point from north to south. Investigation uses iron filings. Filings align with the field. Investigation may also use plotting compasses. Compass needles line up with the field. Opposite magnetic poles attract, like magnetic poles repel. This force acts at a distance. In fact, Earth itself has a magnetic field. This field has a north and south pole. Compasses align with the Earth's field. They point to magnetic north. Magnetic north is near geographic north. Maps include a north arrow. Therefore, a map and a compass enable navigation. But what about electromagnets? A current-carrying wire creates a magnetic field. This field surrounds the wire. A solenoid is a long wire coil. A current through it creates a field. This field matches a bar magnet's field. Electromagnets are magnets from current. The current controls the magnetic field. Switching the current switches the field. Electromagnetic strength can increase. Increased current increases strength. More coil turns per length increases strength, and a soft iron core inside also increases strength. The core material is critical. Soft iron is required. Soft iron magnetizes and demagnetizes quickly. It turns on and off with the current. But steel is unsuitable. Steel stays magnetized after the current stops. This permanent magnetization is ineffective. Electric motors use electromagnets. A simple motor uses a wire loop. This loop sits within a magnetic field. Current flows through the loop. This current creates its own magnetic field. Two magnetic fields now interact. Forces result from this interaction. These forces act on the loop. They act in opposite directions. These forces cause rotation. This rotation is the motor.